Okay, so for this recording, we'll be continuing on with the with other information that we can get from the Michaelis-Menten equation and the parameters that are involved in the Michaelis-Menten equation. So if we look at the enzyme mechanism, okay, so we saw earlier that Km is actually a balance between the rate constants of the reaction rates. Oh, sorry, the rate constants of the reactions that lead to the depletion of ES and the reaction that leads to the formation of ES. So it's K minus 1 plus K2 all over K1. So during conditions when K minus 1 is much greater than 2, meaning the reversible reaction is still playing a significant role, the reverse reaction here. So we're looking at this part of the Michaelis-Menten mechanism. So Km becomes reduced to K minus 1 over K1, and it's actually equal to the equilibrium constant for the formation of ES. Okay, and so we can write the equilibrium constant for ES is equal to E, the concentration of the reactants over the concentration of the product. Okay, so in this form, Km can be taken to be the strength or to indicate the binding affinity of the enzyme to its substrate. So the question is, let's say you have an enzyme that can interact with two different substrates. Because as we saw before, some enzymes are more permissive. They may have a preferred substrate, but they can also react or catalyze a similar substrate. Now, so which do you think will correspond to the enzyme having a stronger affinity for the substrate? Is it a lower Km value or a larger Km value? Okay. So lower Km value signals a stronger or tighter ES complex, meaning your enzyme and the substrate has a larger binding affinity. So the smaller the Km, the tighter is the association between the enzyme and the substrate. Okay? And as you can see from this expression here, we can infer that from this equation here. So your Km will become smaller if the concentration of the denominator becomes larger. And this becomes larger and this will become larger if the binding between the enzyme and the substrate is tighter. More ES will be formed, more ES complex will be formed if the binding is stronger. Okay, so that adds to the interpretation we can give to Km. We can use Km as a measure of binding strength between the enzyme and its substrate. Okay. So we saw earlier that Vmax okay, is equal to K2 times E naught. Okay. In this context, K2 is also called Kcat, or the catalytic constant. So this gives us Kcat being equal to Vmax over E naught. So again, Vmax is the maximal rate. Okay. And E naught is the enzyme concentration that was provided, the total enzyme concentration in your system. Okay, so this is the maximal rate for all of the enzymes, and we're dividing it by the concentration of the enzymes to give us Kcat. So Basically, Kcat, which is also known as a turnover number, it gives us a sort of a measure for how fast a single enzyme catalyzes a reaction. And the reciprocal of Kcat, 1 over Kcat, would on average give us the time it takes for the reaction to be completed. So let's say you're given a a problem like this. So you have a 10 to the negative 6 molar solution of carbonic anhydrase. And so you're able to catalyze the formation of 0.6, and it's able to catalyze the formation of 0.6 molar carbonic acid, okay, per second when the enzyme is fully saturated with substrate. So what's key here? Okay. Take note, stated that you have a rate molar per second, and this is the rate when the enzyme is fully saturated with substrate. So this is actually Vmax. The 0.6 value is Vmax. And you're given 10 to the negative 6 molar solution of carbonic anhydrase. So this would be E naught. Okay. So to calculate Kcat, so you just divide Vmax by E naught. And for the second part of the question, how long does it take to catalyze a carbonic anhydrase reaction? So you just get the reciprocal. So here's a listing of some catalytic constants of some enzymes. So as you can see, carbonic anhydrase is a fast catalyzing enzyme. So it catalyzes around 1,000,000 compared to other enzymes. So the others are have lower catalytic constants. Another information we can gather from measuring Vmax and Km is the fractional occupancy, okay, or the fraction of active sites filled. And the fractional occupancy is equal to V over Vmax and equal to S over S plus Km. So it follows to reason, let's say, because we know, for instance, that if V is equal to Vmax, then that means 100% occupancy. If V here is half Vmax, that means half of the active sites are filled. That's the Km. And if, let's say, V over Vmax is 1/4, so we can assume that that means that 1/4 of the active sites are filled. And then there's the concept of catalytic efficiency. And it's expressed as Kcat over Km. So one reason that why this particular combination of parameters is called catalytic efficiency is, so remember, Km is the measure of the strength of binding between the enzyme and the substrate. Now, does it follow that if the enzyme binds strongly to the substrate, does it follow that its catalytic constant will be faster? Does it follow that it will catalyze the reaction faster? Okay. It can happen that even though Km is large, okay, if Km is large and Kcat is small, okay, so your catalytic efficiency value would be low, okay, compared to an enzyme that has a large Km but also a larger catalytic efficiency, catalytic constant. So in a way, we would describe, let's say, an enzyme that binds a substrate strongly but does not catalyze but its Kcat is small. you would probably describe that enzyme as not very efficient because, I mean, why? I mean, well, because it's already able to bind strongly to its substrate, but it's not able to catalyze the substrate as fast as possible. Okay, so that's why this combination is called the catalytic efficiency. So that's Kcat over Km. And here we have some listings of the different Kcat over Km values of chymotrypsin with different substrates. So if you recall, chymotrypsin is a serine protease and its selectivity is for tryptophan, phenylalanine, and tyrosine. Okay. So its natural substrate, its native substrate are phenylalanine, tyrosine, and tryptophan. It can still catalyze the cleavage of the peptide bonds of other residues, but its catalytic efficiency would be low. Okay. For phenylalanine, it's the fastest for phenylalanine because it's the preferred. So we would say that this enzyme is quite efficient because it binds strongly and it has high Kcat. Now, are there physical limits on the value of Kcat? So if you're going to write the Kcat, the Km and Kcat terms out, we'll get something like this. And essentially what this final expression is saying is that the limit on Kcat over Km is essentially K1. But what is K1? So if you recall the Michaelis-Menten equation or mechanism, K1 is the forward reaction here. Okay. So what it is saying is the catalytic efficiency cannot be faster than the rate at which the enzyme and the substrate can meet, because K1, I'll just write it down here. K1 is the rate constant for this reaction. Okay. It's K1, not K2. Okay. So again, the catalytic efficiency, its upper bound is K1. So essentially, the rate at which the enzyme and substrate will meet, in, I guess, the cytosol through diffusion, okay, would be the limiting rate. The limiting rate for Kcat over Km would be the rate at which the enzyme and the substrate molecule encounter each other in the cytosol. And that would be called controlled by diffusion. So that's why it says here the rate of an enzymatic reaction cannot be faster than the diffusion-controlled encounter. And experiments have shown that diffusion, the rate of diffusion is approached when the diffusion-controlled rate of encounter is approached when Kcat or Km is, well, it's actually 10 to the 7 and 10 to the 9. So meaning, if an enzyme is very efficient, what it means is as soon as the enzyme and the substrate encounters each other, then boom, there's a reaction that happens already. Okay. And some of the fastest enzymes are shown here. So if you take a look at their catalytic efficiencies. It's in the order of 10 to the 7 to 10 to the 9. Okay. And it's said that enzymes that have catalytic efficiencies in this order of magnitude, we say that these are catalytically perfect enzymes, or we say that these enzymes have achieved catalytic perfection. Now, many enzymes do not fit the Michaelis-Menten model. So I think I mentioned this in a previous slide, where again the Michaelis-Menten mechanism, E plus S goes to ES goes to E plus P. Okay. It is an assumption on the part of Michaelis and Menten that the enzyme has only one substrate. Of course, they knew that there are other enzymes that have more than one substrate, but to simplify their analysis, they considered the mechanism when there's just only one substrate. But there are enzymes that do not have just one substrate, and those are included as among the enzymes that do not fit the Michaelis-Menten model. So the multi-substrate enzymes that require multi-step reactions, or the enzymes that have non-hyperbolic reactions. So for multi-substrate reactions, most of these enzymes are oxidoreductases or transferases. So recall what I've always said about redox. If something gets oxidized, something needs to get reduced. And so for oxidoreductases, most of the time there are actually two substrates. One is the substrate that gets oxidized, and the other is the substrate that will get reduced. And for transferases, so their function is to transfer functional groups. Okay? But it has two components. Most of the time it has two components. Transfer functional group from one molecule to another. Okay. So for most transferases, they will have more than one substrate. Excuse me. Okay, so here's an example of a multi-substrate reaction. So this is a bisubstrate reaction. Now, we can still get Km value for the enzyme in each of the substrates. Normally, how that's done is if you want to find the Km between transketolase and this molecule, what you're going to do is you're going to supply this saturating concentrations such that any response to the reaction rate would be coming only from this reactant. Okay, so in that way you can determine the Km between transketolase and fructose 6-phosphate. So once you've determined that, the next set of experiments would be to now provide this molecule in saturating conditions. And so any change in the rate would be only due to glyceraldehyde 3-phosphate. So you can measure the Km of transketolase and glyceraldehyde 3-phosphate. So for these enzymes, there's a Km between the enzyme and a particular substrate. But to measure the Vmax is the maximal rate when both of the reactants are in saturating conditions. So there are different mechanisms for multi-substrate reactions. They can be random, ordered, or there's a ping pong mechanism. Some enzymes need multiple steps to complete a reaction. Okay. So sometimes an intermediate would need to leave before another substrate comes in to complete the reaction. Okay. In this case, it's a bit difficult now to get Km for each reaction, because basically each of these reversible double arrows here will have their own rate constants. And then there are enzymes that do not follow Michaelis-Menten kinetics or hyperbolic kinetics. So these are enzymes that have non-hyperbolic that follow non-hyperbolic kinetics. And normally these enzymes are what's known as allosteric enzymes. And as stated here, allosteric enzymes are those enzymes where there's a site where a molecule can bind, and the binding on that site, that's not the active site, by the way, the binding on this site that's not the active site can affect the conformation of the active site, and in the process affect the binding of the active site to its natural substrate. And for these enzymes that are allosteric, normally they're going to have, instead of hyperbolic curve, they're going to have a sigmoidal curve. Okay, but despite that, we can still apply the same terminologies. Vmax is still the rate that's measured at saturating conditions, and Km is still the substrate concentration that will produce half Vmax. Okay, so we can even compare hyperbolic curves with non-hyperbolic curves.